All right, welcome. And I'm going to continue talking about electrons and electron configurations. Now, I want to show you something kind of cool about, I'm building up to something about the periodic table, really. And it's this. It's sort of going to make a couple connections that we've seen. So a couple things to remember. I'm going to have a whole page of things to remember. So remember, when we look at elements on the periodic table, as they are arranged, as they are in increasing atomic number, we have this regular repetition of the properties, right? So when we look here, we know that anything that's in the same column, in the same group, all have similar properties. So boron, aluminum, gallium, indium, all these all have the similar, not the same properties, but similar properties, similar chemical properties. Okay, something else to take note of. I mentioned that one already. Elements that have similar chemical properties are placed in the same column. Also remember this. So think about what causes elements to have the particular chemical properties that they do. And hopefully you said that it's the electron arrangement in that atom, right? So chemical properties of an atom are dictated by the electron arrangement in that atom. So, therefore, we can conclude that this repetition of, this periodic repetition of chemical properties is due to a periodic repetition of something about the electron configuration, right? So there's this repeating pattern of the electron configuration as well. Now there's something kind of cool. If we look at the periodic table, notice at first there's just this group and then helium, and then we go down and then there's more, and then later on there's more columns. Now think about how this might relate to electron configuration, right? What starts appearing later and later on? Hopefully you're thinking more subshells, right? So at first we only have an S subshell, later we get P, later we get D, later we get F, which is why you start seeing more and more columns. So bear with me, I will flesh all that out. So if we look at the electron configuration of group 1, 1A, so I'm just taking one column and we're going to look at why they have similar chemical properties. So lithium, 1s2, 2s1. And then sodium, all the way up to 2p6 and then 3s1. All the way up to 4s1. All the way up to 5s1. So these all have very similar chemical properties. So what's similar about all of their electron configurations? And there's a couple ways you can frame it, but you're probably all noticing the same thing, which is they all have one electron in their last subshell. They end with this S1, right? Now, they have one electron in their highest energy shell, not just their subshell, but their highest shell, right? There's only, in each of these, so in lithium, there's only one electron in a 2, right? Because remember, the 2 is indicating the shell level. This S is saying what subshell it is within the 2. Well, there's only one electron in 3 in sodium, and 4, the highest, there's only 1 in 5. So they only have one electron in their highest energy shell. And they all end with NS1, N just being the energy level. So it depends on what row you're in. Lithium is 2s1, 3s1, 4s1, 5s1 going down the column. But that's the thing that really makes them all similar. And therefore, they have similar chemical properties. All right, so let's look at group 5A just as another example. 1s2, nitrogen has 1s2, 2s2, 2p3, right? 1s2, 2s2, 2p6, 3s2, 3p3, 4p3, 5p3. So in the same way, we can think, what do these have in common? And there's a couple ways to suss this out. Again, they all end with NP3, N being the shell level. So 1, 2, 3, 4, right? Now, they all end with 3 electrons in that P subshell, in their highest energy P subshell. But now let's take a look at the highest shell collectively, right? So I'm distinguishing between subshell and shell. they all have 3 electrons in their highest energy subshell, which is P, but the shell is all of the things with the highest number out front, the highest principal quantum number. Sorry, I haven't introduced that term. The highest N value. So if you take the P and S together, we can say that they all have 5 electrons in their highest shell, right? 5 here, 5 here, right? Because they both have 3, right? 3, 4, 5. When you get down to arsenic and antimony, it gets a little funkier because they're intersected by this 3D10 in the filling order. But I should point out that 3D is not in the highest shell, right? Why is it? How do I know it's not in the highest shell? It may come after 4s2, but it doesn't have a 4 in front of it, right? It's in the 3rd shell, not the 4th shell. So we're just concerned with how many electrons are in the highest shell, being 4, right? So there's 3 here, but then we look over here and there's 2. It doesn't matter that there's these 10 3D electrons in between. What matters is there is altogether 5 electrons in the highest shell. Down here, 5 electrons in the highest shell. We have to jump over the D's here. So there's 5 electrons in the highest energy shell. So this together causes them to have similarities in their chemical properties. Right? Okay. So these patterns, pretty much, however you want to suss it out, however you want to describe this pattern, right? You could say, oh, they all end on P3, whatever, or how any of the ways I've described it, they all come down to only describing and involving the highest occupied energy level, the highest occupied value of N, right? We don't really care about, it doesn't really matter what's happening down here. These are all full. Everything's full. Only the last shell, is really what dictates the properties, right? And hopefully that makes sense to you because you've got your nucleus, and it doesn't really quite work this way, but as you go higher up, generally as you go higher up in shells, so this isn't how it's going to look, but as you go to higher shells, right, you go farther out and farther out and farther out. So hopefully it makes sense that only the outermost electrons are really going to matter, just like the nucleus doesn't really change or react to chemical reactions, right? This inner shell, these inner electrons, aren't really going to be able to do anything. It's only the outermost electrons that really matter very much. So, in so doing, that's what's really cool about the noble gas notation for electron configuration, is that it emphasizes this highest energy level, right? It just sort of gets rid of all the other stuff. And that's honestly why we use the noble gases as the notation, because they represent sort of representative atom before you go to the next and last shell, right? So when we use noble gases, what we do is we say everything that isn't in the highest shell just is here, and then we can just focus on what really distinguishes that atom and its properties. So we look at the same ones again. Oh, I forgot to put my 1 there. So there should be a 1 right here. Sorry about that. So, 2s1, 3s1, 4s1, 5s1, you can really see why they're similar. And then next one, here. Now, the D's have to come along because they are technically after here, but really they're not in the highest shell. So we see again 5 electrons in the highest shell, 5 electrons, ignoring these, D's, 5 electrons, 5 electrons. Again, I'm ignoring the D's because they are 1 shell number behind, right? So this really isn't in the highest shell, right? And there's a weird thing. It is. I'm not really going to get into it. Just know that this doesn't count for how many electrons are in the highest shell. So we have 5 electrons, 5 electrons. Okay. I'm going to stop with that and then start a new video. So.